David, how would you define and categorize the laws of nature, the laws of physics?
Well, science and physics especially is about finding regularities in phenomena and physical phenomena and trying to explain them. And sometimes if the regularities are regular enough or universal enough or have enough power to explain many phenomena, we call those laws, and we try to construct mathematical theories that unify and bring together these various laws in a coherent fashion. We call often a theory. Now, so sometimes actually what are called laws become consequences of a deeper theory or a deeper law. And in fact, the whole history of physics is one of replacing, pushing back further and further until we have a very succinct and concise set of theoretical ideas from which many phenomena are explained and many previous laws are derived. And so I guess I'm saying partly what is a law in physics is a time-dependent thing. It gets often replaced by a deeper law.
In terms of the concept of law, what about some other relationship kinds of things like causation or logic? How fundamental are these, the flow of time? Are there other kinds of things that are built into the construction of reality that we assume, which may not be true, in order that our common everyday laws seem to flow?
There are certainly many assumptions that are built into all of our successful physical theories that we hold very dearly and sometimes even think carefully about. Causality is one of them. And it, of course, relates to logic. Causality is causality being the principle that event A and causes event B in the past and C in the future and so on. And it is a very strong constraint because if you try to violate the standard notion of causality in physics, you run into logical paradoxes. People would like to believe, for example, that time travel one day might be possible. You could go back and correct many of your mistakes. But then, of course, you run into logical paradoxes. You can go back and kill your grandmother, and then you don't exist. If you don't exist, your grandmother wasn't killed, so you do exist, and so on. So there is a connection often between some of the sacred principles we try to preserve in physics and logic itself, or making sense out of things. But this, I must say, is a bit fuzzy. Physicists and scientists in general are not mathematicians. Mathematicians have a very strict sense of rigor, definition, and proof, whereas physicists are much more practical and pragmatic. If something works, doesn't really matter, whether it violates some preconception, it works. We tend to believe that something that's illogical isn't going to work. And so far, we've been correct with that. But what we really care about is if it works. We make observations of nature, we try to explain those and fit our understanding and test it. And people have been willing, therefore, to consider the violation of almost anything that you can, imagine or state precisely, including causality, including just about everything. so far, they haven't found any way to construct, theories in which causality is slightly violated, so you wouldn't notice it with observation. But in general, people have been willing to give up almost anything. In some cases, have been forced to. After all, we went through only 80 years ago a revolution in physics with the birth of quantum mechanics that forced us to give up some of the absolute obvious assumptions that we made about physical reality. And so I have a feeling that if it were to work, we'd be willing to give up any principle you could possibly imagine.
What about symmetry? That's one of those abstract principles, seems to come from mathematics, that has a very significant impact in the world of particle physics, with the need for symmetry and then broken symmetry. How does it work?
I think in a way, in physics, one could say that the 20th century was the century of symmetry, starting with Einstein's understanding of relativity, special relativity as a symmetry of nature, and proceeding through the development of the theory of elementary particle physics, which is based on, to a large extent, on symmetries. So you're right that symmetries are sort of an abstract, beautiful, mathematical notion that is very aesthetically appealing. But in the 20th century, mainly, we discovered and understood how basic symmetry is to the structure of nature, not just in the fact that we discover in nature many symmetrical objects, and not just the fact that the laws of physics tend to be unchanged by various symmetry transformations, rotations, get the same phenomena if you rotate the laboratory. That's a symmetry transformation. But in the modern theory of particle physics, we have learned that in a much deeper sense, symmetry underlies the actual dynamics. It explains why forces exist, even why particles exist in the patterns they do. So it's one of the reasons we've been led more and more to believe that whatever nature is, it's awfully beautiful. And for some reason, nature and our ideas of beauty, or the laws of nature, the structure of the patterns that nature exhibits, and what we regard as beautiful tend to coincide. It's quite pleasing.
There are even studies that show that facial features, the more symmetrical they are, the more we subjectively value them as beautiful.
Yeah, that's a very interesting sociobiological. I'm not sure that, I suppose, there must be some people believe, or we believe that there's some correlation between physical beauty and health or something, some reason.
But it's interesting to see the concept of symmetry aesthetically, mathematically, abstractly, and now in the world of particle physics, being almost a general theory that pervades so many different, not only orders of magnitude, but so dissimilar kinds of ways of thinking.
And one of the most interesting aspects of that is how the very notion of symmetry has evolved through the last 100 years. In physics and in mathematics, now step in step, our understanding of what, so there are many symmetries that we're accustomed to seeing visually, as you say, we see in people's faces or in works of art. But mathematicians, and with the use of mathematics, one can imagine symmetries that are vastly richer and actually even more beautiful, if you don't mind. And that expansion of our understanding of the scope of beauty of symmetry, and it continues to grow.
And then we have the next step, which is broken symmetry. We see that in some kinds of art,
Indeed.
and we also see it as a requirement of fundamental physics.
Right. Though it's a little different. In art, one of the requirements, I gather, of Islamic art which was very geometrical, that if you designed a very symmetrical building, like the Taj Mahal or something, you had to put in a little bit of imperfection and make it slightly break this otherwise perfect symmetry. Otherwise, you would offend Allah. But in physics, we have something we call broken symmetry. It's a little different. We have situations that show absolutely no sign of symmetry at all. They're not just little imperfections. There is no sign in the visible state of the universe, of the system, of asymmetry, such as us sitting in this room. The laws of physics are invariant under translations. So if we move everything 2 feet, the laws of physics will be, if I do an experiment here, or if I move 2 feet and do the same experiment, I get the same result. But this room is not translationally invariant. I'm here, you're there. The state of this room is not translationally invariant, even though the laws of physics are. Well, we might expect that of this room. After all, we put things into this room. But when we look at the vacuum, the empty state with nothing in it, nobody's done anything, nobody's modified it, and we discover that even though the laws of physics are totally symmetric under a beautiful symmetry, that structure of that vacuum state, which is not featureless, it's a lot of stuff that characterizes the vacuum state, is not symmetric. That is a inherently different situation, which is why those new symmetries are hard to discover, and why they can actually be many more new symmetries that we haven't discovered. If they hadn't been broken, they would be evident. So we now invent symmetries all over the place because we say, undisturbed by the fact that there's no direct evidence for them, because we say, well, they can be broken. And if they're broken, we can look for regularities, but they're not manifest regularities. They're much subtler, but very powerful, as powerful as if they were explicitly manifest.
There is a common feeling that when we have mass, we see things that have mass, we have mass, that we instinctively know what it is. But an understanding of fundamental physics shows that our intuitions are not necessarily correct.
Yeah, I mean, for example, one of the nicest advances in our understanding of that occurred, 30 years ago with the theory which I was involved in, the theory of the strong nuclear force. That's the force that holds the quarks together, makes up the nucleus that makes up the center and the mass of the atoms that we're all made out of. So, and those quarks actually are almost massless particles themselves. So if we now understand where most of your weight comes from, maybe 95, 96% of your mass is simply energy. So you remember Einstein taught us that E equals mc squared. If you have a massive object, you can extract a lot of energy from it, like nuclear reactions. But the right way, the other way you can think about that formula is that mass is simply energy. And now we understand that our mass, our weight, is simply the energy of these quarks that are being held together by this nuclear force and confined to live within this nucleus. And all of your mass is simply confined energy. It's all E over c squared. You are made out of energy. The quarks could be massless. And if they were massless, you would lose about a few pounds. Wow. All the rest is confined energy.
So what people normally think of, who know a little bit of atomic physics, that the nucleus has all the weight.
Yes.
When you go in the nucleus, you have protons and neutrons. Now that's the weight.
And the proton.
Then you go inside the proton and the neutron, you have 3 quarks, and you think that that's all the weight. And now
The quarks have no weight at all. They're just running around, so they have a lot of energy. And they're being pulled by this force, which also has energy stored in it. That adds up to give all the weight of the proton, of the nucleus, of you.
So the formula is not just something in theory, that the energy that is really occurring there among almost massless things,
Yes.
that energy is then translated into mass.
Yes.
That's really remarkable.
And we even understand why, from that point of view, why gravity is so weak. Because according to this theory of quantum chromodynamics, what's holding them together is a force that gets strong at some distance scale. Now remember, the characteristic distance scale was this Planck scale, very, very teeny. That's where gravity is strong. The scale of the neutron and the proton is where this force, this nuclear force, becomes strong. And if everything is unified at the Planck scale, we can calculate in QCD, in this theory of the strong force, of the nuclear force, how the strength of the nuclear force evolves as we go to larger distances. What we discovered was it gets bigger, but it gets bigger very slowly, logarithmically. And
it's like a rubber band.
Yes, but it starts out very, very weak and very slowly gets bigger. Whereas the force of gravity starts out strong and very slowly, very rapidly gets weaker. So we can actually calculate that fact that we have to go up by 20 orders of magnitude in distance before the force that holds the quarks together gets big enough to provide the nucleus.
Wow. But this also seems to circle back to the origin of cosmology, because if everything is now energy, when we go back to the very beginning, that's where it all started from anyway, that it was all energy going through some transformation into matter. But when you look all these levels deep, you find that the matter itself is a small part.
Yeah. So really, energy and matter are not different. That's what Einstein taught us. And indeed, already in the case of the nucleon, the proton, the nucleus of your atoms, that's already, as we now understand it, quite manifest.